So everybody who's ever used a homotopy solver will probably scratch their head and say, what's this guy talking about, using fluid equations with a homotopy solver? Homotopy solvers are lucky if they get 25 equations and do well with them. And they're usually pretty darn slow. But it turns out that there's a fellow that we've been working with at UIC who's gotten homotopy solvers, who's shown that homotopy solvers are really good solvers for anything that's quadratic. And so in taking care of a lot of these equation by equation ideas, we can actually use these in any formulation that gives us a quadratic PDE. And so then, all right, so why should I care? Well, one, we want to hit multi-level because multi-level will make an optimal. Two, we have processor flops are increasing faster than bandwidth, as Scott showed us earlier today. So homotopy methods all work on a path at a time, and if you have a whole bunch of different processors that can work on a path at a time, you have a lot of work and very little communication between them. We can have nonlinear algorithms that can be efficient, more efficient than these linear algorithms, just because right here we can use these bandwidth to our acknowledge. Now, the problem is that right now we have lots of these equations have so many flops that this hasn't been realized yet, and it also presents an opportunity for another field that's been growing very rapidly in the last 5-10 years. And so we believe that there's a really good opportunity for these polynomial solvers. They have better, we think we'll have better performance at the end of the day, especially once we go to multi-core chips. And I mean, if you want to start using really big algorithms, you're going to start thinking about these sorts of things anyways, whether or not you think about them in a homotopy solver or not. That's going to be what we have to do. We say it's more robust. And we say it's more robust just because we get all solutions to our problems. Whether all solutions are really necessary or not is questionable, but just the fact that there are more than one solution begs the question, why shouldn't we try to find out what a few more of those are? And we don't even know what the algorithms will be at the end of the day, because we've already kind of seen where we solve these equations and we get 6 different answers, and building trees and discovering which answers are good and bad is kind of a thing we're still working with. So we have a prototype, and the prototype's pretty, I coded it up, so it's not something you want to read. It's kind of a humble little thing we have, and maybe as it grows it'll get better. But right now we have FEM assembly for the full nonlinear tensor, which is something I don't think FEniCS has been able to do yet, but I don't think it's that hard to put in. We have some small test problems, and we have a couple of different polynomial solvers. When we first started, we thought we'd just use Sage because it's easy interface. Everybody can download it and you go real quickly, but we learned real quick that we couldn't use it because it's a lot slower than we had expected. But we solved a good number of problems with Sage. And now we're also onto this FEC pack by Jean Verschild at UIC, and it has a lot of potential. Right now we're solving about 500 degrees of freedom with it. 500 is not a lot, but it's a place to start. Our new prototype, this slide should really be called If I Was Using FEniCS. I'd love to actually use UFL as my surface language, use maybe Dolphin as a better meshing and some hierarchical methods, which we don't really have built into Dolphin too well, I guess. But Peter might be working on that, I don't know. And so just some of our test cases of what we have run on this. Did linear forms, because you can't solve a linear form, you can't solve a nonlinear form. We have some made-up equations, just for testing multiple solutions. And then we threw in Navier-Stokes right now. The next bullet that's coming in the next month will be several Oldroyd equations. Like I said, these are small but exact, but we have lots of ideas of how to increase these this number of degrees of freedom. Just to give you, once again, the comparison to Newton. Yes?
Exact, you mean solving the discrete system?
Yeah, exactly. We do have the discrete system exactly. Meaning you give me an FEM discretization, I'll solve all nonlinear equations on top of that. So I mean, it's not exact in the sense that, you know, any possible order you want, but it is exact in the fact that it'll beat Newton, where you don't really have any idea of how good the answer is at the end of the day. So comparison to Newton, so if you use Newton with multigrid, you have a good nonlinear solves. You have simple interfaces software library, but you have low computational efficiency. There's very little we can say about how long that Newton will take to converge. And in fact, we can say it can be arbitrarily bad for some places, but it takes quite a while to figure out which places. As the flip side is our multigrid, which hasn't really been developed too much, but well, multigrid FAS has been developed, but with a homotopy solver, not as much yet. We have good nonlinear solves, lower bandwidth, and potentially a high efficiency, meaning we know how long it will take to solve an equation. We've known since the 70s, but we've just ignored it because it's so long to do it in the 70s that maybe it's realizable today. But one thing that we can certainly do to make it solve bigger systems is start looking at smaller systems on the fly and bring them into bigger systems as well. So my conclusion, make it a pretty short talk. We have nonlinear effects really plague simple models, and even these simple models where you just want to know a little bit about your problem before you start building the big system. It would be really nice to have an idea of what your solution space looks like that often you don't get elsewhere. Better numerical experiments are possible. We always know this. This is why we keep working. I mean, and I'll be sure to keep everyone posted if I have any more. I mean, we're working on the paper to write up our simple model, but we're continuing our efforts to use these homotopy solvers. And hopefully Jan Verschild will help us make it much, much faster on the homotopy side.